So welcome back. In the previous week, we have reached till the divide and conquer approach of the algorithm design, and we have seen two different approaches which the merge sort uses. The one we call as two-way merge sort. It is basically an iterative process of doing the merging among different lists to find finally a sorted list. And this is the approach which we use, and the total time complexity of merge sort algorithm was n log n. Now, the actual merge sort, which is a divide and conquer method, means the merge function is recursively called each and every time in order to do the merging. And if you see the pseudo code of the merge sort, this is nothing like two-way, four-way. It is just the recursive process, the divide and conquer. It's not iterative. The actual function we pass two arguments, which is the first element of the array which we need to merge, that is low, and the last element of that array which we assign as high. Then we say that if low is less than high, so since it is a divide and conquer approach, we say that if low is less than high, then it is a big problem, which means that there are more than one elements in the array. If low is not less than high, it is either equal to high, then this problem is a small problem, because when low and high are pointing towards the same memory location, it means there is only one element in the array. And in such a situation, we call it as a small problem and we solve it. But when this condition becomes true, that low is less than high, it means there are more than one number of elements in the array. So we treat that as a big problem. And once it is a big problem, we split it. This is what the divide and conquer approach actually does. It breaks a big problem into small, multiple number of problems, and then solves each and every small problem, finds its solution and combines. So how we divide it is that we find a mid element, mid of this array using this formula, and then we again call this merge sort recursively. But the thing which we are changing is we change the parameters which we are passing to this merging function. That is, we call the merge sort again. Now the parameters are low to mid. That is, from the first element to the mid, mid will become the partitioning, and again do the merge sort from mid plus 1 to high. So we keep on dividing it, dividing into small chunks, into small elements. And once this merge sort is done, means the first merge sort will sort the elements on the left hand side of the array. If it is of 10 elements in the array, the 5 first elements will be sorted. The next merge sort will sort the elements from the mid to the remaining highest number of elements. And then we call this merge function. And merge function, I have already discussed that when we are having this A element which is sorted A list, another sorted list B, then how we merge that into another array C which is also in sorted order. So this merging is this merging which we finally call. This pseudocode will be called, and the two sorted lists which we get from calling the merge sort will be then finally merged into third array, and that will be the final merge. Now, in the iterative process, I have taken an array of size 8 elements while we discussed about the two-way merge sort. and we will take the same array with same elements, but we will not apply the two-way merge sort, but we will just apply the merge sort, which is the divide and conquer approach. So here is this array with 8 elements from 9, 8, 7. This is not in sorted order. And now we will apply this merge sort on this array. Since it's a divide and conquer, and every divide and conquer algorithm works under the principles of recursion. And whenever you see the recursion, automatically the stack should come in your mind. Every recursive function uses the stack to store the temporary data. So let's focus on this example. Initially, when we call this function merge sort, the two parameters which will be passing is low and high. Here, low is L, the first element. High is 8, the last element. I have written H and L here in place of low and high. So when we firstly call the merge sort, we will pass this 1, which is low, and this high, which is 8, to this merge sort. So low and high, 1 and 8 will be passed, so it will be compared if low is less than high. If 1 is less than 8, yes, the condition is true. So find a new value which is equal to mid. So mid will be equal to L plus H, that is low plus high divided by 2. 1 plus 8 means 9 divided by 2. So I have written it in the form of this. This is known as tracing, that what elements we are passing to merge sort in different elements. And then what happens? In the first iteration, I am passing it 1 which is low and 8 which is high. So forget about this remaining tree, just focus on this one, 1 and 8. So in the first iteration, I will be passing it 1 and 8. And it will now find out the middle element, 1 plus 8 divided by 2. That is 9 by 2, that will be equal to 4. Okay. And 4 is this index. It is not this data, it is this index. So that is why I have written mid here, which is pointing to 4. Okay, so we have found mid, and now we will look to pseudocode again. So when this is less than that, we find the mid. When we find the mid, we again recursory call merge sort. And in this new calling to merge sort, we are changing the parameters. We are giving it the parameters from low to mid. So now this low is again the same, that is 1, and the mid is now 4. Yes, so we pass new arguments to it, that is 1 and 4. Sure. And similarly, one more recursive call will be given to one merge sort by passing the parameters mid plus 1 to high. Mid is this thing 4, so mid plus 1 will become 5, and high is equal to 8. So we are recursively calling the merge sort and are giving it the new parameters 5 and 8. So now from here we have reached to this part and to this part. Again, when we pass 1 and 4 to it as the parameters, so this merge sort, this one, low comma high mid, the control will go back to here again, because this is the calling function. Inside it we are calling this, we are recursively calling these sub functions. Now low will be passed as 1 and high will be passed as 4 for this part of the array, because this is divided into 2. This will become a separate array, this one will become a separate. So we had to do merge sorting for this element, this array, and we will again compute it as low and compute it as high. Low will be equal to 1 and high will be now equal to 4. So we will pass these new values as 1 and 4 to this. Again, it will go inside, is low less than high, is 1 less than 4? Yes. So this condition will become true again, and mid value will be calculated again. Now mid value will be calculated low plus high divided by 2. Now in this step, our low is 1 and our high is 4. Are you following me? So mid will be calculated 1 plus 4, that will equal to 5 divided by 2. So that will be equal to 2. So that is why I have put down these yellow marks here, which means that initially this whole array is 1. Then when we do the first iteration, it is divided into 2. This part becomes half, this part becomes half. Then when we pass 1 and 4, it is again divided into 2. This left array is again divided into 2 more sub arrays. By finding the mid will become equal to 4 plus 1, that is 5 divided by 2, and that will be equal to 2. So this will become the new mid. Again it will be divided, that this part of array will be treated as a separate and this will be treated as a separate recursively. Because in divide and conquer, our approach is the same, that to divide large function into small. So on passing 1 and 4, what we are doing is that we are finding the new mid. New mid becomes our what? 2. All right. Similarly, on the right hand side, when we recursively call this function merge sort, mid plus 1 to high, our mid initially was this 4 when we first operated this merge sort function. So mid plus 1 will become 4 plus 1, that is 5 will become mid plus 1. So we will treat it as low for this part of the array, and high will again become equal to 8, that was already high for this part of the array. So that is why we are passing 2 more parameters. This mid plus 1 will become low for this array, that is 5, and this 8 will become high for this array, this one. So now we have divided this big array into 2. This becomes left part, this becomes right part. So again we will call these two functions merge sort and merge sort, two functions recursively. Now going to the left hand side, when we recursively call the merge sort, so what we do is that we again find the mid. As I said, 1 plus 4 will become 5, and 5 divided by 2 will become equal to 2. So our new mid value will be 2. Are you following? Take now this till here we have divided into 2. This becomes 1, this becomes 1. So let me colorize it. So till this part, these two, we have divided this array into 2. This one is on right side, this one is on left side. So when we are passing 1 and 4 as the new parameters to this merge sort, it will again compare low less than high. Yes, it will again find mid will become equal to 2, this part. When mid is equal to 2, so what we do is that we again go to this part of the function. We recursively call merge sort, but changing the parameters. Now the new parameters we are setting it is low to mid. Low, so this array is again divided into 2 more arrays. Okay. So this whole array is divided into 2. This becomes 1, this becomes 2. For these two elements, this array, 2 becomes its mid. Okay. And when we recursively call this function, the merge sort low comma mid. So low will be again 1, and mid we have found 2. So we again recursively call by passing the parameters 1 comma 2. And on the right hand side of this thing, right hand side of this array, these are these two elements, we pass mid plus 1. Since mid is equal to 2, mid plus 1 will be 3. So 3 and high of this array, that is 4. 3 and 4 will be passed on the right hand side. Similarly, when we go to this part of the array, which is on the right hand side, we again recursively call the merge sort by passing the elements mid plus 1 to high. Mid was initially 5, So initially 4, so mid plus 1 will become 5, and high was already 8. So we pass 5 and 8 to this merge sort. So this 5 and 8 will be passed again to this merge sort. This will become 5, this will become 8. It will go inside. Is 5 less than high? Yes. Find the new mid value. The new mid value will be 5 plus 8. That will be how much? Shavash? I'm talking about this array. This left part is for this left subtree is for this array which we have traversed. Now we are in this right array, and this right subtree is for this array. As this was initially the first mid, this is mid plus 1. 4 plus 1 means 5, and this is high. And we are calling this function mid plus 1 to high, means from 5 to 8. We are in this part of the array. So this array is as a whole. We pass it 5 to 8, that is from this to this. And when we pass those elements, the control will go back to this merge sort. Low will be as 5, and high will be now again as 8. So 5 plus 8 will be equal to 13. 13 divided by 2, that is 6. That is this. Okay. So we reach here, and we again, when we calculated the mid value, the new mid value, we again call this merge sort. Now the merge sort will be again from new low to new mid. The new low for this array, this one array, this will become the new low for it. The next merge sort, this will become low, that is 5. And this will become the new high for it, which is the mid value, that is 5 comma 6. And on the right hand side, on this side of this or right hand side, we will call again recursively this function mid plus 1 to high. Yes, you are having any problem? Come here. So this will become the left hand side. On the right hand side, we will be passing the parameters mid plus 1 to high. So mid is now 6. So mid plus 1 will become 7, and high is again 8. So we pass 7 to 8, 7 to 8. So now we have reached again, this right array is now divided into two more arrays. Let me colorize it different. So till first level, second level, and third level, this level, we have divided the array into these different chunks. So now again, when we are here at this point, that is our array size is 1 to 2. Two elements are there. In the new iteration, that's iteration number 3 or 4, our low is equal to 1 and our high is equal to 2, only focusing on this green part. So now we have divided our original array into 1, 2, 3, and 4 arrays. So we will apply the merge sort on all the 4 arrays differently, starting from the green one. For green one, our low is equal to 1 and our high is equal to 2. So to do pseudo code, we will pass low equal to 1, high equal to 2. So low is less than high. Yes, the condition is true. So again, find the mid. Mid will be, for this array, the mid will be the parameters which we are passing 1 and 2, they are mid. 1 plus 2 divided by 2, that will be equal to 1. Okay. When 1 becomes the new mid, so this will be the mid. L is pointing to 1, mid will be also pointing to 1 for this array. When it is pointing to both the low and mid are pointing to the same memory location, we go for merge sort. Merge sort from what? Low comma mid. So merge sort from 1, this is the first element, and this will be the second element. So we are again divided this array into two more sub arrays. One will become, this will become a separate sub array like we did. So let's colorize it differently. And on the right hand side, this will become mid plus 1 to high. Since high is again 2, mid plus 1 is also pointing to 2. So this is just one element. So it will be divided into one element, 2 comma 2. Because mid plus 1 is 2, high is again 2. That's why we are passing the memory location of a single element. Means we are dividing it into individual one element. Now we will shift ourselves to this part, that is the second array. Similarly, for second array, this will be the control flow. Initially, its low will be equal to 3. That's why we are passing 3. And its high will be equal to 4. That's why we are passing 4. We will again find low plus high divided by 2. 4 plus 3 divided by 2. That will be 3. Okay. And when we pass 3 to it, so for this part, this element, its low was 3 and its mid is again coming to be 3. So divide it into one element, 3 comma 3. Similarly, for this part, it's mid plus 1, that is 3 plus 1, that will be mid plus 1, and it is high, that is also 4, divided into 4 comma 4. So again, we have divided this array into two more arrays. Similarly, on the right hand side, this will become low, this will become high. Find out the mid, 6 plus 5, 11 divided by 2, that's 5. So we will pass low as 5 and mid will be passed as 6. Then when we find one more mid, that is 5 plus 6, we will again divide this array into two arrays like we did it here. So this will be this array will be taken as a separate and this array will be taken as a separate individual elements. Now the only remaining is the last array of two elements, 7 and 8. Its low is 7, its high is 8. 7 and 8 we pass. So find out mid, 8 plus 7, 15 by 2, that will be equal to 7. So that mid and low is both 7. So it is a single element. Mid plus 1, 8. That 8 and high is again a single element. It is single element. So finally, our complete array is divided into 8 different elements. And this is the working of merge sort. Now the actual merging, the first merging will start from here. This element number 1 and this element number 2. That is this array which is divided into one. This is one array, this is one. Now we will use this approach. Individual element will be compared with each other. This 9 and 3, whatever is lowest, that will be brought to the first. Now we have divided into manageable small chunks. We will compare and we will perform the merging. We will perform the sorting. So this 1 and 2, the element at location 1 and the element at location 2, those will be evaluated with each other. And whatever is smaller, that will be brought. So in these 2, 3 and 9, 3 will be kept first and then the 9 will be kept at the second stage. This will be the first merging. All right. In the same way, if you go to this from this root to left side here, and we have checked its left side. Let's check its right side. That is the root of 1, 4. Since this 3, that is this element, and this 4, that is this element. So the element at location number 3 and element at location number 4, both will be evaluated. Is 5 greater than or less than 7? Since it is less than, so it will be merged. 5 will be kept here, 7 will be, this will be the second merge. So initially we started from 1, 8 root, we moved like this, left, then we traveled here, moved to right. Once it is done, we merged, we reach it here again. Then we go to the right part, then to left of this right, then to the right of this right, then we reach it back to here. So when we did this second merge, we reached to this place. Now we are having two sorted arrays. This is sorted, this is sorted. We need to merge. That's why you see this merge function at the end of this program. This merge function does the same function which this merging we have already done. How it does when we are having two lists, how it merges them into third sorted list. So already These two are sorted. So the merging is called, and it will then do the third merging here by merging this list and this list, but in sorting order 3, 5, 7, and 9. This will be the third merge. So that means this subarray, this subarray, this subarray, this subarray, this left part is all merged 3, 5, 7, 9. Now we will go to the right side. Again, on the right hand side, this is the small problem. This is the small problem. So element at location 5, element at location 6, those will be merged. At 5, we are having 4, we are having 6, and at 6th location, we are having 4. So 4 is smaller, 4 will be kept firstly, so this is the fourth merge. On the right hand side, element at 7 and 8, this is 2 and 8, 2 and 8, so ascending order, this is the fifth merge. Now this is sorted, this is sorted. We reach to the another stage where both those sub arrays, that is this array and this array, those will be sorted, calling the merging function. So this is 2, 4, 6, and 8, the sixth merge. When this one becomes sorted, this one becomes sorted. So the final merge will sort or merge those two sorted arrays 3, 5, 7, 9, 2, 4, 6, 8. Final merge, the seventh merge will be performed here, and 2, 3, 4, it array will be then printed or displayed in the sorted order. So is it visible? So if we again look to this tree, this is known as tracing. So we are doing the tracing of this algorithm. We see the actual merging starts from this level, because till now we were dividing, then we evaluated these two, and the first merge started at this level, this level, this level. So how many elements we merged is n, because total elements were 8. Then we went back to this second level where the next merging was done, and in this level again n elements were merged. Yes, and then the final merge was performed on this root node of how many elements? Again n. So in total n merge elements were merged here, n were merged here, n were merged here. To find the total number of levels we need, we had to find out the height of this tree, which we found out here. Okay, and height of this tree will be found at, it's like we are initially having n elements, we are merging here, elements we are merging here, elements we are merging here. So the height of this tree, if we see it here on this previous example, we saw the first pass, the second, we are dividing it to a 2, and finally the height of this tree was coming out to be log n by using this formula, 8 divided by 2 divided by 2 divided by 2. When we finally reach to, this whole should reach to equal to 1. So we can write it 8 divided by 2 power n is equal to 1. So 8 will be equal to 2 power n when we cross multiply, and n will be equal to log. In this case, it will be log 3 to the base 2, because we are having 8 elements. 2 power n, 2 power 3 is equal to 8. So for general formula, it will be log k to the base 2. So that is why we are taking it log n to the base 2. So the height of this tree, tracing tree, is equal to log n, and number of merges which we are doing is n. So this is the total time this algorithm will take. Log n, height of the tree, and number of times or number of merges which we perform, that's n. So n log n is the total time complexity of merge sort. Even if you perform it iteratively, which is known as two-way merge sort, its time complexity is n log n. Even if you use merge sort using divide and conquer, again its time complexity is equal to n log n. And we have traversed this list or this array using the addresses using the indices of the array, because initially we are passing 1, that is the low, at 8. This is not the data which is present in the array, because at location 1 the data is 9 and at location 8 the data is 2. So initially we traced this algorithm using the indices of the array. In this example, I have done the same thing, but I have traced it using the data. So like I am giving it initially the array this, then when I make the first call on the left hand side, I will be passing it this array 2, 3, 4, 5. This is not in ascending order. This is the final result I have written it here. So I will be passing this array to it. The final array I will get will be the array which is in sorting order, like this. So instead of writing so many intermediate steps, I have written this as a final output of this merge sort, just to demonstrate one thing. And what is that thing is that initially I am passing this left array to this merge sort, this whole left array. Then on this side I am passing this whole right array. Then when I go to left hand side, I then divided this array into 2 more. So in the left hand side I pass these 2 elements, that is from this to this, and on its right hand side I pass these 2 elements. Okay, then when I do this dividing, I then start doing merging. Merging is done at this location. These 2 elements are merged. So I go from here to here to here. Then I do their merging and their value comes here. So the point here is I start from this array. I go downwards like this. Then I reach to this leftmost element. I traverse, go to the right of one. Then I find the values of these 2 and I come here. 3, 9. Here the first merge is done, that is element 3 and 9 are sorted. This is the first sorted. Then I reach to this node again and go to this right node. When I reach to right node, I again divide it and reach to its left node, that is 7. From 7 I go to its right node, that's 5. I evaluate these 2 and merge. 5 is coming first, 7 comes first. So this is sorted, this is sorted. Then I go back from here to this path and merge these 2 sorted lists, 3, 5, 7, 9, these 2. And then I shift back to the right side and I traverse it in the same. Firstly go to left side, then to right side, then to root. Then to left side, then to right side, then to root. Then to root and then to root. This is the actual traversing I do in merge sort. And this type of traversing is known as post-order traversal. You might would have seen these different types of traversals are present in a graph, like in order, pre-order, and post-order. Post-order traversal is left, right, and root. So when we start from left, then we go to right, and finally we go to root. That traversal is known as post-order, and it is very important that the merge sort follows the post-order traversal. And this is the pseudocode. This pseudocode I have written again here. Now to find the recurrence relation of which we are actually used to of merge sort algorithm, let's keep it as Tn. That is the total number of time this whole algorithm will take. And in this pseudocode, I am recursively calling this merge sort twice. But the parameter I am passing is n by 2 because I am dividing the array into 2 halves, 2 sub-components at each iteration. That's why this recursive merge sort, its parameter gets divided by 2. Similarly, this recursive merge sort, its parameter gets divided by 2. So the total merge sort is divided into 2. And 2 more recursive functions we are defining. Then final merge, again one more function is merging. And this merge is doing the merging of all the n elements initially passed to this merge sort. Okay. So if I find out the recurrence of merge sort algorithm, you see the recurrence will be T of n is equal to T of n by 2 plus T of n by 2 plus n. So that means 2Tn by 2 plus n. And this happens when n is greater than 1. When there are more than one number of elements in the array. That's one why it becomes a big problem at that very time. But when it is equal to 1, means there is only one element. When n is equal to 1, so we assign some constant value to it, that it will take 2 seconds, 3 seconds, whatever. So the actual recurrence of merge sort is T of n is equal to 2Tn by 2 plus n. So as I said, you do the sorting using any one of the techniques, two-way merge sort or merge sort. The complexity of this algorithm is always n log n. Now, if we try to solve this recurrence of merge sort using any one of the methods we discussed, maybe the recurrence tree, maybe the substitution, or maybe the master's method. The recurrence is 2Tn is equal to 2Tn by 2 plus n. And now for the time, we use the master's method. A is equal to 2, this, B is equal to 2, this, function is n, this, whatever is on the right hand side, that is f of n. So we find log a to the base b. So that will be equal to 1. Our k is equal to 1. That is the power of whatever is power to this n. So our log a to the base is equal to k. Because this is coming out to be 1, this is coming out to be 1. Both the terms are equal. When both the terms are equal in master's method for dividing functions, this is a dividing function. So it comes under case 2. And when it comes under case 2, we go and find the value of k. Since k is here 0, so it comes under subcase 1. Because in case 2, there are 3 cases. So out of those 3 cases, it comes under subcase 1. And subcase 1 gives the solution that whenever you are having a function like this, you find those parameters and the total complexity of that algorithm will be order of n plus p log p plus 1 n. So substituting value of p here equal to 0, you find it is equal to n log p plus 1, that will again be equal to 0 plus 1 times n. So order of n log n. So even if you try to find out its complexity using the recurrence method of solving the recurrence equation, you will find it equal to n log n. And for your recap, I have taken one of the slides when we were discussing about the recurrence relation, and there we have taken this kind of recurrence as an example. We have taken this program code calling the test function twice by dividing the parameter n by 2 times this. If you are not old, you might would have remembered this recurrence we solved. And when we found the recurrence of such a program code, we found it is equal to this 2n by 2 plus n. And I have even written it that it is very important a recurrence relation, even in that slide then when we were discussing. And its solution comes out to be n log n for such a relation, recurrence. So since merge sort is also having the same recurrence, its complexity will be also order of n log n. Did you find Chaitanya? Did you find it? So now this was about the pseudocode. Let's do some analysis of this algorithm in the today's lecture. This is very, very important. And if you take any one of the papers of any competitive exam, the previous papers, you will always find the questions related to it. So the analysis of merge sort means to find out its advantages and disadvantages. The first important advantage of merge sort is that, and again for your kind information, I am making those whole slides myself. I had to sometimes sleep at 1 o'clock for this purpose. Because if it would have been offline, I would have simply prepared my lecture and would have noted it down on the board. So I had to also prepare it. I am not copying it from any net or any Google site. So pay attention because this is very important. So the merge sort is the suitable algorithm for doing the merging for large number of elements. If we are having millions of the records or millions of the data, and you have been asked to find out or to sort this data in a particular sorting pattern, merge sort is the best sorting algorithm among all the sorting algorithms. There are n number of sorting algorithms. You take example of merge sort, quick sort, insertion sort, bubble sort, bucket sort, radical sort, count sort, wo sort, ye sort. There are so many sorts. So whenever you find n number of records, that's million number of data are there, no algorithm beats the merge sort. First thing. The second thing is that merge sort does not apply only to list or arrays. The merge sort is performed even on the linked list. So I have taken an example here. Two linked lists are there, 2, 8, and 12. S is another 3, 9, and 11. So to perform merge sort on such a linked list means that 2 will come here. It will remain as such. And since after 2 and in between 8, this 3 comes. So the links from 2 to 3 will be changed. Initially the 2 was pointing to 8. Now its link will be changed and 2 will be pointing to 3. Then 3 will be pointing to 8. There will be no direct link between 2 and 8. So this can be also done by the merge sort. By using the merge sort, we can even sort the linked list. Now the actual most important application is the external sorting. Merge sort is that sorting algorithm which supports the concept of external sorting. And now we will see what does that mean. External sorting is that this is a secondary storage device, a hard disk or any secondary storage device which is having space or storage capacity in terabytes. Why you are sleeping? Come here. So you are having a secondary storage device. Suppose its capacity is 10 terabytes. And we are having 3 files, F1, F2, and F3 on the secondary storage device. And there are different records inside this file F1. One record is of 2 size, the another record contains 10, the another contains 20. Similarly, the file 2 is having different number of the data inside it. This contains the size of 3, 5, and similarly. And the total size of this file F1 is 5 GB. Total size of this F2 is 10 GB. And the size of our man memory is 4 GB. We have been asked to do the sorting of these two files, F1 and F2. So in the operating system, I am mentioning it continuously that we can't perform any operation on the secondary storage because this is just a storage. This is not memory. Memory is that part where we can both store as well as execute. We don't do any execution on the secondary storage. So we have to bring this F1 and F2 into this man memory and perform sorting here. This is RAM. Since the file size of F1 is 5 GB, the file size of F2 is 10 GB. So 10 plus 5 will become equal to 15, but the space of our man memory is only 4 GB. So we can't do it here. So in such a situation, what we do is that we take the first data file or data element of file F1, that is this 2. We bring it here. We take the first element of F2, that is 3. We bring it here. So only these two will be brought, not the whole file. So when 2 and 3, that is the first two elements are brought, those are evaluated. Whatever among them is smaller, we sort it. Since 2 and 3, those are evaluated with each other, the 2 is smaller. So we take this 2 again, put back into external storage device, into another file F3, and keep this 2 there. Okay, so we cross this 2 because it is already done. Now we take the next element from this file F1, which is 10. We take this 10, brought it into main memory. Already the F2 element 3 was present there. We evaluate 3 and 10. Whatever is smaller, it is 3. We take it back from main memory and put it in the external storage device in the ascending order. So 2 is cross, 3 is cross. From F1, we are having 10, and we bring another element from F2, which is 5. Similarly, we take only one element at a particular time, do the sorting, and push it back into the secondary storage. This way, our merge sort does the sorting of such a huge amount of data in a limited amount of memory and stores back the data in the original secondary storage device, whose storage capacity will be 5 plus 10. So this F3 will need 15 GB of the memory. And this way of doing the sorting is known as external sorting. And merge sort is the one algorithm which supports this concept. So we are discussing about the advantages or maybe the pros of this algorithm. The final important is that it is a stable algorithm. Merge sort is a stable algorithm. And what does stable mean? That if we are having an array like this with element as 8, 6, 4, 3, 8, 5, 9, the next 8, this 8 means that the 8 is repeating. There is a duplication in the data, duplication in the student records. So after sorting, when I do the sorting of this array, my result should come like this. So since this small 8 was coming before this large 8, so after sorting, this small 8 should again come before this large 8. Since both are equal, so I have only changed it its font size. And when such a situation, the algorithm which follows such a situation, maybe in case of these numbers, it won't get justified. What is the reason? What is the benefit? But when you talk about the actual data, that is the records of the bank employees, the student records, this type of information, that is this record should come before this, even after sorting, is very important. So when order of duplicates is maintained, such type of algorithm is known as stable. It follows the stability property. So we will finish its cons, and that will be the end of this merge sort. So those were the advantages. These are the disadvantages. The first one is that it takes extra space. Extra space means that this is important here. It is not an in-place sorting algorithm. There are two types of algorithm based upon their working: in place and which is not an in place algorithm. Merge sort is not an in place sorting algorithm. In place means what? If sorting is done in same list, if we are having an array here, array, if we take this 9 out, bring 3 here, kept this 9 here, then compare 9 and 7, take 7 out, keep it in a variable, keep 7 here, then take 9 here, which means we are sorting the elements in the same array. So the original data which was present in array A, the sorted array, the sorting we are doing in the same array. Just taking one element, comparing it with other elements and finding its exact position. That algorithm is known as in-place algorithm. So the original position of the elements is maintained and sorting is performed. But merge sort does not follow this principle. That's why it needs an extra space. Every time it divides the original array into subarrays, we need to store those subarrays somewhere. Then subarrays somewhere, so subarrays somewhere. Only when we do the final sorting, then we can put back the sorted array into the initial original unsorted array. But the intermediate results, we need the extra space for that. That's why this sort of algorithm is not in place sorting. But again, the interesting case is that this is not in place in case of arrays, but this is in place algorithm in case of linked list. You see, I had taken the example of linked list here. I did not find any extra space. I did not need extra array or extra linked list. The only thing I need to change is to change the links, change the references. I was having the linked list of size 3. I merged it into a linked list of size 6. It was also 6. So only changing the links, in place sorting algorithm for linked list, but not for arrays. Very important. Okay. Now the another disadvantage is that if we are having a data array which we have to sort, and that is of small size, the merge sort does not perform well. It will give you the results in sorted array, sorted order, but it will take more time as compared to its other competitors in the market. The other sorting algorithms which are present in the market, the merge sort is having less performance when the size of the data which we have to sort is less. So for small number of elements, merge sort is not a good choice. That's why I said here when discussed its benefit is that it is the only sorting algorithm which can sort millions of data elements at a single time. But for small data size, it is not a good choice as its performance degrades. And it has been seen in the research that when the size of the array is less than or equal to 15, when we had to sort 15 number of elements from 1 to 15 whatever, merge sort is slower than the other algorithms, maybe the insertion sort. So if we are having an array of size 15, we apply insertion sort and merge sort to it, insertion sort will be faster. But as soon as the size of n gets greater than 15, nothing can beat the merge sort. And recursive, as I said, every divide and conquer algorithm follows the recursion, and every recursive function needs the stack, because recursion means that we are doing the depth first analysis, we are doing the depth first search. We make a root, then the root calls subroot, that subroot then again calls it a subroot, and this subroot and root, it keeps its data, it keeps its records, it keeps its progress stored somewhere in the stack, because when the control comes back to the calling function, it should be able to find out to which extent it has already done its work. That intermediate results is all stored in stack. The intermediate results which a recursive function stores in calling another recursive function is stored in an extra space stack that is known as activation record, and height of that stack will be equal to log of n. In addition to it, it also needs another auxiliary array, which is known as auxiliary array is needed for doing the, when we do divide and conquer, we divide original array into subarrays. That subarray is a different array. That subarray is again a different array. So we need those auxiliary arrays. And auxiliary array size is again equal to n. because we are dividing n elements into n sub elements. So stack size needed will be log of n. Auxiliary size of array will be needed n. So the total merge sort takes n plus log n space. So in terms of space, since it is recursive in nature, it takes a little bit more space than the other sorting algorithms in the market. Okay, this is all about the very important divide and conquer merge sort algorithm, its tracing, complexity, recurrence, pros, cons. So I will stop it here for today's lecture.